GPE and Escape Velocity. The expression GPE equals mg delta h only works near the surface of and is specific to the planet. So here's little g, universal gravitational constant, mass of the planet, and then the radius of the planet. As an object's height above the surface of a planet increases, its distance from the center of the planet is not just the radius of the planet anymore. Thus, a more general expression is needed based on Newton's universal gravitational force equation. This time, the force will be g m planet m object over r squared, where r planet dash object is the distance from the center of the planet to the object. Deriving a more general formula for the potential energy of an object that moves further away from the Earth requires calculus, because the gravitational force is not constant. It must be integrated, which is a type of calculus, over the distance the object moves. We'll just present the result here and use a more common physics term for gravitational potential energy, U sub g. Why do you think there's a negative sign there? When using calculus to find the potential energy, and hopefully you'll stay around for AP Physics C where we'll do that, an assumption was made that the gravitational potential energy between two objects an infinite distance apart is zero. The negative sign means that the gravitational force is always an attractive force. Now, how can we reconcile this negative sign with the fact that we normally think of GPE as a positive number? Here's our function. What does that look like on a graph? Well, here's the radius of Earth, right over here, and out here would be infinity. This is how far the object is from the center of the Earth, for example. And this is our potential energy, and it's negative. So GPE measured for objects near the surface of the Earth is mg times hf minus h0. And it's normally right around here, okay? And you set h0 equal to 0. It's the change in height above the Earth's surface that is important. GPE is not an absolute number. The graph shows that as r, this is r, as that increases, the distance from the center of the Earth increases, the object moves above the surface of the Earth. Ug, the potential energy, will be less negative. So for example, if here, let's just give a number. That's going to be, let's just say minus 10 joules. As it moves further away from the Earth, this would be, let's say, negative 5 joules. So when we do the final minus initial, we have negative 5 minus a minus 10. That gives you plus 5 joules. So the difference between the final potential energy at this height minus this one is going to be positive. So mg delta h will still be a positive number when you're near the Earth's surface. Now apply this expanded definition of GPE between two masses for the calculation of escape velocity. Escape velocity is the minimum velocity an object, such as a spaceship or a rocket, needs to attain to escape the Earth's gravitational pull. Actually, since the force of gravity has an infinite range, this is never really possible, but the force will be extremely tiny at great distances. And we're going to use the conservation mechanical energy for the Earth spaceship system. To obtain the minimum required velocity to escape the Earth, the rocket should arrive at infinity with zero total mechanical energy, which is the sum of kinetic energy and gravitational potential energy. This is so the least amount of fuel can be used by the rocket to get to infinity. Gravitational potential energy has already been defined as zero at infinity. So here's our conservation of mechanical energy. This is our original, and this is our final at infinity. So we're trying to find escape velocity, so that would be 1/2 mv squared, where v is the escape velocity, minus the potential energy at the surface of the Earth. Now, GPE is 0, and so is kinetic energy. We want to get there with the minimum velocity. So we multiply both sides by 2, take the square root, and we get the escape velocity right here. Escape velocity is independent of the mass of the escaping object. It only depends on the mass and radius of the object being escaped from. So in this case, we're talking about Earth. Using this fact, can you explain why, despite the fact that hydrogen and helium are the most abundant elements in the universe, there are only trace amounts of each element in our atmosphere? When the Earth was first formed, the atmosphere contained significant amounts of both elements. However, hydrogen and helium are the lightest elements, so for a given atmospheric temperature, they would move faster than the heavier elements. Over time, their average speeds exceeded the escape velocity of Earth, thus they left the planet. Why can't the expression GPE equals mgh be used to determine the GPE between the Earth and a weather satellite in geosynchronous orbit above the Earth? Satellite's orbital period? Nope, nothing to do with that. You don't care about the speed, but here's the point. The value of G is different at the Earth's surface and at the satellite. The answer is C.